Okay, in this problem, notice we're given a piecewise defined function and asked to discuss the discontinuities that are present in that function, and we'll have to classify each as either removable or non-removable, and we'll need to describe graphically what is going on at those points. So let's copy this function down to our paper so we can look at things in more detail. Okay, here's our piecewise defined function. So how do we find those x values that create discontinuities in the graph of f of x? Well, remember what it means for a function to be continuous at a point. Essentially, three things have to happen. The limit as x approaches the c value in question has to exist. The function itself has to exist at that c value. Remember, the limit says nothing about what happens at a particular value of c that x is approaching. And then those two values, the value of the limit and the value of the original function, have to agree. So if we're looking for discontinuities in this function, we're looking for values of x, c values if you will, where one of these three things, or more than one of them, fails. As far as where to look, of course we need to look at each piece to see if one of these three things fail. We also need to look between the pieces, where the function changes. This is frequently the case because when you bring two pieces together, two random functions together, sometimes they do indeed join up in a nice continuous manner, but they often miss each other entirely as well. And so if we were looking at this particular value of c, for example, we would see that the left limiting height and the right limiting height disagree. Of course, if the two one-sided limits, the left and the right limit, disagree, then the overall limit at x as it approaches c fails to exist, and we have a gap discontinuity. So we want to be very careful about what happens here at the borders between pieces. We'll definitely want to check those x values out. Okay, so let's start a list. Let's start a list of all the x values that we'll need to check. Certainly x equals 0, the border between these two pieces we'll need to look at. X equals 2, the border between these two pieces we'll need to look at. We also want to look for any domain or limit issues in the pieces or within the pieces themselves. Let's look at this bottom one. Is there an x value here that causes us some worry? Well, sure there is. X equals 4 would cause a 0 in the denominator. That's a domain issue. That's going to violate this number 2. Now be careful. It has to be a relevant domain issue for us. It has to agree with this condition on this piece. And of course, 4 does. 4 is bigger than or equal to 2. So it makes our list. But had this been, say, x minus 1, even though 1 would cause a 0 in the denominator for this guy then, it doesn't satisfy the condition, so it's of no worry to us. Okay, but 4 does satisfy the condition, so we add it to our list to investigate further. Looking at the second piece, well, this is a nice linear piece, right? A linear function. A linear function's domain consists of all reals. You can find their limits very easily. Being polynomial functions, their limiting value and the functional value should both exist and agree. This is a continuous piece. Looking at the top piece, however, we're a little bit concerned here when we see the possibility of taking square roots of negative values. What happens if x gets too large in magnitude? Now mind you, we're talking about x values that are negative to begin with, but that's okay. If we square them, they still get bigger. What happens when we square negative 6? You get 36 minus 36, which is 0. If you square anything less than negative 6, right, more negative, then this goes negative. And you're out of the domain of this expression. So at x equals negative 6, the domain simply stops. That might be something for us to look at a little bit carefully. Maybe we just write a little note to that effect to remind ourselves of what's happening there. So we have potential discontinuities at these 4 values, but they shouldn't occur at any other x value then. barring perhaps these things that are left of -6, where there's no function at all. We know some of them will definitely be a discontinuity, for example 4, because the function's not defined there. Other values, like 0 and 2, we're not sure yet, but we have to investigate all of them thoroughly to figure out whether we're talking about removable or non-removable discontinuities, whether we're talking about gaps or vertical asymptotes or holes or whatever. And to do that analysis on each one of these things, you may find it useful to use a different but equivalent definition for continuity, namely this one. We say f is continuous at x equals c, same thing as above, if all three of these things exist and agree in value. Notice if the first thing and the last thing, the left and right limits as x approaches c, if they both exist and agree, then this first condition is satisfied, and vice versa. And of course, if either one of them then agrees with f of c, and f of c exists, you've picked up the second and third conditions. And that goes the other direction as well. So let's use this bottom equivalent definition for continuity in our discussion. Let's also create a table to organize our thoughts. Keeping in mind we'll need to know the values of all three of these things, or at least what's happening to all three of these things. The c values that we want to consider, of course, are these x values here. So let's fill those into our table. We'll want to consider 0, and 2, and 4, and -6. Let's take 0 to start. What's the limit as x approaches 0 from the left of our original function? Of course, for this limit that we're talking about x values that are very close to 0, just left of it, so just negative. Which of these three pieces applies in that situation? It would be the first piece, right? So we can rewrite this as the limit as x approaches 0 from the left of the negative square root of 36 minus x squared. Now, what is that? Well, a brief inspection of this expression and knowing the limit laws involved tells us that we can find the value of this limit just by plugging in 0 here, and we get negative square root of 36 minus 0, or -6. So let's put that in our table. Now, what is the next thing here? F of c, f of 0. Well, which piece applies? Notice no piece applies when x equals 0. In a very subtle way, 0 was left off of our domain. This is undefined. The limit from the right, however, moving over to this box, which piece applies here? What is f of x if we know our x value is just to the right of 0? Which piece applies? Well, there we're just to the right of 0, so it must be this piece. So we can write this is the limit as x approaches 0 from the right of 2x. But that's a polynomial, so I'm free to plug it in. And I get 2 times 0, or simply 0. So let's add that down here. Now we have some follow-up questions here. Are we talking about a discontinuity? And if we are, is it removable or non-removable? And what's the graphical interpretation? Well, notice we're definitely talking about a discontinuity. What was required of these three things to be continuous? Those three things had to be all exist and agree in value. Notice this doesn't exist and these two do not agree in value. To decide between removable or non-removable, we need to ask ourselves the question, does the limit as x approaches c exist? Of course, that only happens if both of those things exist and agree. In this case, those two things are those two things. They don't agree, so the overall limit does not exist, and so we're talking about a non-removable discontinuity. To find the graphical interpretation, sometimes it helps to use this information to draw a super quick graph of what's happening right around x equals 0. This tells us, coming in from the left, we need to be getting very close to a height of -6. So our graph is doing this. Notice this piece of information doesn't tell us what happens at x equals 0. And in fact, looking at the next piece of information, we know that there is no point on our graph associated with x equals 0. It is undefined there. Moving to the right here, coming in from the right, coming in this way, it appears we need to be getting arbitrarily close to a height of 0. So let's draw a point at height 0 there, and we're coming in from that direction. Maybe we come in from above, maybe we come in from below, and the same thing here. Maybe we're coming down to it, maybe we're coming up to it. That's not terribly relevant if all we're trying to do is classify the discontinuity according to its graphical interpretation. What is important here is I have jumped from down here to up here, creating a big gap between the two. So that's my graphical interpretation. I have a gap discontinuity or a jump discontinuity between these 2 points. Okay, let's move on to the next c value in question. X equals 2. Here are the 3 things I'm after, in those 3 boxes right there. What happens as I approach 2 from the left? What function am I really taking a limit of? For these values, just shy of 2, it would appear this condition applies, and so this is the function in question. Of course, then this is the limit of a polynomial function, and I can just plug this value into here to get a 4. So we'll write that down here. For f of 2, I need to again come down here and ask myself the question, which piece applies to x equals 2? Well, there's the one with the equals. So I guess we need to plug in 2 here. So that would be -8 on top over -2, which looks like it's going to be 4. So let's write that here in our table. Lastly, up here, the limit as x approaches 2 from the right, so we're a little bit bigger than 2. Which piece applies? Again, this bottom piece. So I need to figure out what is the limit of this expression as x approaches 2. But of course this is a rational function, which is continuous on its domain. And that means I can evaluate the limit at a point like 2 that doesn't cause a problem with the domain just by plugging it in. Well, that's the same thing we did last time. And we got 4. So let's write that down. Now, are we talking about discontinuity? And if we are, is it removable or non-removable? And what's the graphical interpretation? Notice this is not a discontinuity. We got the same value in all 3 places. All 3 of these things existed and agreed in value. And so our conclusion here is we have a point of continuity at x equals 2, not a point of discontinuity. So we can move on. What about x equals 4? What's the limit as we approach from the left? What's the value of f of 4, and what's the limit as we approach from the right? In the first case, when we're approaching 4 from the left, we're just a little bit shy of 4, a little bit less than 4, like 3.99. Which piece applies? Well, that's bigger than 2, so it looks like this piece applies. Now, what's the limiting behavior? If we're very close to 4 but a little bit less, notice the bottom is very small, right? Think 3.99 minus 4. It's very small and it's negative. The top, however, if x is very close to 4, maybe a little less, this is still going to be very close to 16, maybe a little less. And 16 times 2 is very close to 32, maybe a little less. Of course, then we're negating that. But we're still going to be very close to negative 32. And as x gets closer to 4, this thing here only gets smaller. So what's happening in the limit to this whole fraction? This is getting very big, isn't it? And the negative there and the negative there cancel to give us something positive. So this is getting very large, and it is always positive. for these values of x. What we're seeing here is an infinite limit take shape. So let's mark that. Now, moving on to the next box here, or this value here. What is f of 4? Here again, which piece would apply? Well, 4 is bigger than 2, so I need to plug it in here. But what happens when I attempt to plug it in? I get 0 in the denominator. So this function is not defined at x equals 4. So I'll make that remark in my table. Now, what about the last one? The limit as x approaches 4 from the right. You're a little bit bigger than 4. So like 4.01, getting closer to 4. Well, this behaves a lot like the left-sided limit. If you're a little bit bigger than 4, like 4.1 or 4.01, this is still a very small value. The only difference now is it's positive. As for the top, we're still very close to negative 32. But whether we're a little bit above negative 32 or a little bit below doesn't make a whole lot of difference. It's not going to change the sign, like being a little bit above 0 or a little bit below 0. But taken together, you're dividing negative 32 by a smaller and smaller thing, which in terms of magnitude is getting very, very large. And in terms of sign, notice this is now negative. So it looks like we're flying off to negative infinity here. So we'll mark that in our table. Now, is this a discontinuity? Do we have a discontinuity at x equals 4? Certainly. Even though we put these two expressions in here for those two limits, technically they do not exist. We violated one of the conditions of continuity. And further, because they are infinite, because the one-sided limits were infinite, we have the presence of a vertical asymptote. So, is it removable or non-removable? Again, this depends on whether or not the limit exists. The limit certainly does not exist because it involves infinity. So this is definitely non-removable. And as far as a graphical interpretation, and drawing this frequently helps. Let's say here's 4. As I approach 4 from the left, my height, my function values, need to be flying off to positive infinity. As I approach 4 from the right, the height of my function has to be going down to negative infinity. And you can guess here what we have. And I mentioned it before. We've got a vertical asymptote. Okay, so we'll indicate that in our table. Finally, we get to x equals negative 6. What's going on here? Well, if I look at the three things again, and ask myself the question, what happens in the limit as x approaches negative 6 from the left? Of course, if I'm left of negative 6, then this top piece applies, because I'm negative, and this x squared is bigger than 36, so when I do the subtraction, I have a negative under the square root. That's out of the domain. It really doesn't even make sense to ask this question. The domain issues are preventing us from finding any value for the limit here. That said, at negative 6, it's not a problem. Negative 6 meets this condition, so we use this piece, we plug in negative 6, and we, of course, get the square root of 0, or 0. And likewise, as x approaches negative 6 from the right, again, to the right of negative 6, you're talking about like negative 5.9 or negative 5.8. Now subtracting that away from 36 isn't going to cause a problem. Everything's good. We can evaluate the limit by plugging it in, and we again get 0. Okay, so what do we say here? Technically, because these three things did not all exist and agree in value, this one of course being the one that fails, we don't have a point of continuity. We could say it's discontinuous there, although we write this in a little bit different way. Because the function simply stopped at negative 6, and the function doesn't even exist to its left, we really just focus our attention on these other two. And noting that they both exist and agree, we can say at least this. It's continuous from the right. That's not continuous, but it's still nice in a certain sense. Now we're ready to write up our discussion of the discontinuities of our function, which this table summarizes. So let's move this out of the way and slide things up a little bit here. So first off, notice that we had a point of continuity here, so that's not really relevant to our discussion. And this one we're kind of ignoring as well. This is a continuous from the right situation because the function suddenly stops. But the other two x values, 0 and 4, both cause discontinuities. So let's start there. We notice there is a discontinuity at x equals 0. It was non-removable because the left-sided limit and the right-sided limit disagreed in value. So the overall limit failed to exist at x equals 0, or as x approaches 0. And the graphical interpretation was a gap. So that's how it graphically presents itself. And again, this is due to the fact that the left and right limits disagreed, even though they did exist. We also note that we have a discontinuity at x equals 4, so we write that down. We classify it as non-removable, citing why it's non-removable. Remember, the limit failed to exist because both the one-sided limits here were infinite, and in fact just one of them being infinite would be sufficient to cause the problem. And finally we say something about the graphical interpretation here, that we created a vertical asymptote. Okay, so we write that in there. And that is our discussion. We're done.